So this video is going to be in both the calculus playlist and the real analysis playlist, and in this video we're going to look at the epsilon definition of a limit, the formal definition of a limit, what it means for a sequence of real numbers to converge to a limit. So let's start by talking about what a sequence is. So intuitively, that's not the pen, intuitively a sequence is something like this, where we might call our sequence the sequence A, so we'll denote the terms by A with a subscript, and then the first term we can denote A1, the second term we might denote A2, or not might, we will, third term A3, etc. The nth term will denote AN, and then it just goes on and on forever, where all of these A sub n's are going to be elements of the real numbers. So that's what intuitively a sequence of real numbers means. Formally, it's a function, so we can say that our sequence A is a function from the natural numbers into the real line, if we're talking about a sequence of real numbers. So what this is saying is that every element of the natural numbers is being mapped onto some real number, and indeed the way this will work is 1 is being mapped onto whatever A1 is in the real line, 2 is being mapped onto A2, 3 is being mapped onto A3. So this function is going to encode actually the exact same information as this intuitive picture that we have of a sequence here of this just sequential terms going on and on forever like this. So this function will encode the same information. Now note, the natural numbers normally include 0. That is a little bit controversial. Some mathematicians actually don't like defining the natural numbers to include 0. They want it to be 1, 2, 3, 4, 5, 6, all the counting numbers without 0 included. However, I think the majority of mathematicians agree that we'll use the natural numbers as all those counting numbers plus the number 0. And indeed all the constructions, the von Neumann or Zermelo constructions of the natural numbers, they include 0. So I think it's widespreadly accepted that the natural numbers does include 0. There is a bit of controversy there. However, you'll notice that I haven't, in my sequence, actually included a 0th term. That's just personal preference. Loads of people do include a 0th term, so you might also see sequences like so, A0, A1, A2, etc. So the first term of the sequence is going to be the 0th term. I prefer to just drop that 0th term and have the first term called A1. And the main reason I actually like that is because one of the classic sequences that we always go to in real analysis as an example would be the sequence given by 1 over n. This is called the harmonic progression, or less commonly the harmonic sequence. So on a picture, this sequence looks like so. So the first term is going to be 1 over 1, which is just 1. The second term will be a half. The third term will be a third, a quarter, fifth, you get the idea, and on and on. So on the picture, the first term is here, 1, and then the second term is a half, then a third, and then I'm not going to draw anymore because it'll just clutter up and it won't really mean anything, but you get the picture, they're all getting closer and closer to 0. So this is a very famous sequence that we use all the time as an example. It's called the harmonic sequence, or more commonly the harmonic progression. Progression means the same thing as sequence. So this, obviously, if you try and plug in 0 to here, it's nonsense. So you would then have to define your 0th term by some other rule, some random rule. You might have to just set it equal to 1, or I suppose you could set it equal to 2, or whatever you like. But that's just messy. Because we use this so much, I actually just prefer to go from 1. And also it feels more natural to call the first term A1 rather than A0. But be aware that that means that really I should, in this formalization of what a sequence is, I should have that it's the natural numbers take away 0 if we're going with my use of the sequence where we're starting from 1, 2. So it should be the natural numbers without 0 mapped onto the real line. However, as I say, you will see loads of people doing it with the full natural numbers and they have a 0th term. But in this video, we're just going to start at A1. So we want now to talk about the concept of the limit of a sequence, and I'm sure you're all familiar with the notation. Limit as n approaches infinity of a sequence an is equal to, and we'll call our limit L. What does this mean? So hopefully you've got some intuition as to what this means already from naive calculus. A brilliant place to go as an example is to the harmonic progression. So we'll go back up here. So you can see these terms of this sequence, they're getting smaller and smaller and smaller. You know, the millionth term is going to be 1 divided by a million, so 0.00000001. I hope I've said enough zeros. So it's getting smaller and smaller and smaller, closer and closer and closer to 0. However, it's never going to reach 0. There is no n that you can put in here, no natural number that you can stick in there that's going to suddenly divide to become 0. It's also never going to cross over into the negative numbers. For all of the natural numbers, they're all positive numbers, so when you take their multiplicative inverse, that's still going to be a positive number. So it's just getting closer and closer and closer and closer to 0, but never actually getting there. That's the intuitive concept of the limit of this sequence. So we would say that the limit of this harmonic progression, limit as n approaches infinity, of 1 over n is equal to 0, because that's the place on the real line that the terms of the sequence are getting closer and closer and closer to. So what we're now going to do is try and actually use that intuition to motivate the epsilon definition of a limit. So let's go with this. So we want to capture the fact that the terms of the sequence are getting indefinitely close to this limit L. And the way that we do that is we say that for all, and why am I using the blue pen? That's not going to show up very well. Let's get rid of that. I was trying to make it a little bit more colourful, but white shows up so beautifully. It's the go-to colour. So for all epsilon greater than 0, and this is the reason it's called the epsilon definition, because we use this Greek letter epsilon classically. Do not use any other letter for this idea here. You could use any letter, but this is the letter that everyone uses, and people will look at you as though you are mad if you don't use it. So for all epsilon greater than 0, so take any real number that's greater than 0, in the example of our harmonic progression, where the limit is 0, you should be able to now put an interval, an open interval, around that 0, the limit value, or in this case 0. So the boundary here is epsilon, and the boundary here is negative epsilon. And it should be the case that no matter how small you make this, so if we make a smaller interval, and we could make it even smaller still, so we could make this smaller and smaller and smaller, it should be the case that no matter how close you get to the limit, there should be terms in the sequence that are that close to it. This is how we're going to capture this idea that the terms of the sequence should get indefinitely close to the limit. Now, I'm initially going to write down a wrong answer for what the epsilon definition is, based on what we've just said, and then we're going to see why it's not the right thing to do. So it should be the case that for all epsilon greater than 0, there should be a term. So what can we write here? There should exist a, shall we say, x, oh no, we're using a as our sequence and not x. And there should exist a, let's say n is an element of the natural numbers. And by the way, this is wrong. I've said that already, but I just want to stress that I'm writing down something wrong to show you why this isn't good, and then we'll get to the final one. So there exists some element of the natural numbers, so some term in the sequence, such that the distance between that term, an, and the limit is less than epsilon. So if you're confused by what that means, it means exactly what I've said on the picture. So if we now have a general limit, L, I'm saying that no matter how close you want to be to the limit. So pick for any epsilon, it should be the case that you can find a term in the sequence, so there should exist some term in the sequence, that's all this bit's saying, there exists some little n in the natural numbers, such that if you go to that term of the sequence, the an, and look how close it is to the limit, it would be less than epsilon, so it would be in here, so that's this term an. So that's capturing this concept of we want the terms of the sequence to be indefinitely close to the limit. Because no matter, you can make this epsilon whatever you like, and I'm saying that there should be, you should be able to find a term in the sequence so that it's that close. So this is, if you like, a formal way of capturing this idea that we want the points of the sequence to get indefinitely close to the limit. However, this is not the final definition of the epsilon definition of a limit, and we'll see why this is broken now. So the flaw in my little definition here is as follows. Let's consider another sequence, which is going to be a modified version of the harmonic sequence. So I'll keep the first term, and I'm going to rub that out because it's in the wrong position. So I'll keep the first term, 1, and I'm going to get rid of that second term, a half, and I'm going to replace it with something I want it to be. And I'm going to replace it with 20, and then I'm going to keep the third term, so we'll have a third, and then the next term, a quarter, I'm going to throw that away again, and I'm going to replace it again with 20. And then I'll keep the fifth term, so 1 over 5, and then I'll get rid of the sixth term, I'll replace it with 20. So overall I'm going to get rid of all the even terms and replace them with 20, and I'll keep all of the odd terms. So my sequence, an, is going to be defined as follows. It will be 1 over n if n is odd, and then it will be 20 if n is even. Let's have a picture of this. So here we have 0, here we have the silly number 20, and then not to scale, in fact I'm going to go even more off scale. Let's say this is 1, so it's an absurd scale, it's almost logarithmic, but because I want to show things in detail here, we need more space on the picture ascribed to this part. So I hope that doesn't bother you. So this is a third here, and then there'll be a fifth here, and then etc. So this sequence goes as follows. It goes 1, then it goes to 20, then it goes to a third, then it goes to 20, then it goes to a fifth, then it goes to 20, and it gets indefinitely close to 0 on the odd terms, and then all the while it's flitting back to 20 forever and ever and ever. It continues flitting backwards and forwards between something that's converging to 0 and then something that just sits at 20, 20, 20, 20, 20. Now, this sequence, it is not true to say that this converges to 0. The limit of this sequence, this limit of this thing, the limit as n approaches infinity of an is not equal to 0, and it's not equal to 20 either. Both of these points are limit points of the sequence, but overall it doesn't have a limit. It's not correct to say it has a limit. If you like, it really has two limits. It has the limit of 0 and the limit of 20. They are both limit points of the sequence, but in order for a sequence to overall have a limit, it has to only have one limit point. If you've got a sequence, for instance, I could take another example. I could take the sequence 1, 2, 3, 1, 2, 3, and I could repeat this pattern on and on forever. So it just alternates between 1, 2, and 3, 1, 2, and 3, etc., on and on. That in a picture, if that's 0, that's 1, that's 2, that's 3, literally just flits between these three forever. Goes there, 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 there. And again, this sequence does not have a limit. It's not correct to say it has a limit. It has 3 limit points, but it doesn't have a limit overall. And it has Also, if you're familiar with the concept of a subsequence, it has 3 convergent subsequences, and indeed this one up here has 2 convergent subsequences. In fact, they have more than 2 and 3 respectively, because you could take different types of subsequences and still get to the same limit. But they have 2 separate limits that subsequences can converge to in the case of this one, and 3 different limits that subsequences can converge to in here. So I'll just go a little bit off track. I didn't actually intend to talk about this, but since we're here, let's do this. So if we just talk about the concept of a subsequence, A1, A2, A3. So we've got our general sequence back again here. So a subsequence is where you go along your sequence, and for each of the terms you decide, do you want to include it or not? So for A1 you can decide include or not include. So maybe I'll decide I want to include A1. And then for A2 I decide include or not include. Maybe I decide not include. A3 I decide, do I want to include it or not include it? Maybe I decide not include. And for these ones that I don't include, hopefully it's reasonably obvious that I'm not including them in my new thing that I'm constructing here as a subsequence. And then let's get to A4. Maybe I decide I want to include that, so I put A4 in. And then it goes on like this. So a subsequence is where you're going along the sequence and it's kind of a subversion of the sequence. That's a bit of a tautology that I've just said there. But literally you just decide which of the terms you're going to include and which you don't. You have to keep the terms in the same order. So if you like, you can view it as you could imagine putting all the terms of the sequence into a great big set, so the set an, where n is an element of the natural numbers. And then a subsequence is going to be a subset of these, but when they're actually rearranged into the sequence, they have to be in that same order that they were originally in. So for instance, you can't suddenly have, I don't know, A5, A2, A1, A6, A7. That's nonsense. That's not a subsequence, because the order of these terms that are appearing here isn't the same as the order that they appeared in the original one. So you have to keep them in the same order. So looking back up at our examples, which is the reason we got into this discussion in the first place, in the case of this one, you can take the subsequence that just contains these values of 1. So it can have this one, and then we'll choose to not include this, not include this, include this, don't include this, don't include this, include this, don't include this, don't include this, include this. So it's going to be this pattern of include, and then 2 don't includes, include, 2 don't includes. And that would be a sequence of just 1, 1, 1, 1, and that does have a limit. That's 1. And then you can do the same for the 2s and 3s. So this sequence has 3 different limits that the subsequences can converge to. And it was, previously I said that there were 3 different subsequences. That's not quite true, because if you think about taking a subsequence that converges to 1, we could actually include a finite number of non-1 terms. So we could, for instance, have, maybe we don't include this one, we do include this one, we don't include this one, don't include this one, don't include this one, don't include this one, and then from now on we do include, don't include, don't include, include, don't include, don't include. So then it would just be a sequence that initially has a 2, and then every term after that is 1s, and that will still converge to 1. So that's another example of a subsequence that converges to 1. So it's not that there's just 3 subsequences that converge, it's that there are 3 different values that subsequences of this can converge to. So even though there are convergent subsequences, it's not true to say that overall the sequence converges. It doesn't overall converge. And it's the same with our example up here. Again, there are 2 different limits that the subsequences can converge to, but overall the sequence does not converge. Now, why did I even bring this silly sequence up in the first place? Well, the problem is it highlights what's wrong with my attempt at a definition for what is meant by convergence to a limit, because it would satisfy this. All this is saying is that if L is the limit of the sequence, 0 in this case is our hypothesized limit, then it has to be true that points or terms of the sequence get indefinitely close to our limit L. And it is true that terms get indefinitely close to 0 in the case of this sequence here. So because we've still got these odd terms, they do get indefinitely close to 0. So you give me whatever epsilon you like, however small you like, I can actually find you a term of this sequence that is within that epsilon ball around 0. As long as epsilon is greater than 0, there will be such a 1. So all I need to do is find 1 over n so that it's less than epsilon, and we know that n is going to be odd. So I just need to find an odd number that's like that. So now basic inequality properties, I can multiply both sides by n, I can multiply both sides by the multiplicative inverse of epsilon, and we then get that 1 over epsilon is less than n. So all I need to do is actually find an odd natural number that's greater than 1 over epsilon. So 1 over epsilon is going to be some positive real number. It might be a very large positive real number because epsilon might be absolutely tiny. You know, it might be 1 over a billion or something absolutely tiny. So its multiplicative inverse might be something absolutely enormous. However, hopefully you will agree that it is always possible to then find a natural number that's bigger than whatever that number is. And indeed, it will be possible to find an odd natural number that's bigger than that. And in that case, 1 over that natural number will then be less than your epsilon. And so you've satisfied this definition for all epsilon. I can find you a term of this sequence that is within that epsilon interval around 0. Formally, what we're using here is the Archimedean property. And I should not be writing this down. Am I going to spell this correctly? I believe it's spelled like that. The Archimedean property of the real numbers, which says that the natural numbers are not bounded inside the real line, i.e. there is no real number that is bigger than all the natural numbers. And the proof of that is actually quite simple. It follows straight away from the least upper bound property. I might just, for interest, give a little outline of that. I apologise if there are viewers who aren't aware of what the least upper bound axiom of the real numbers is. If you're not aware of that, just zone out for a moment and we'll come back to the epsilon definition of the limit shortly. So it's a simple proof by contradiction. If the natural numbers were bounded, then there would be a least upper bound to them. So we could call that S. And that follows by the least upper bound axiom of the real numbers. So it's a really important axiom of the real numbers that defines them. But this is a problem because what you can now do is you can consider, so if we have a picture, we're imagining this number on the real line is now an upper bound for all the natural numbers. So it's greater than or equal to every single natural number. It's also the least upper bound. So what that means is you can consider taking s minus 1, and s minus 1 can now not be an upper bound of the natural numbers. Otherwise it would contradict s being the least upper bound. Therefore there must exist a natural number that is bigger than s minus 1. So it's going to be in this gap between s minus 1 and s. So there's going to be some n, which is an element of the natural numbers, in there. But then you can just consider n plus 1, and you'll get that n plus 1 is then greater than s, because n is strictly greater than s minus 1. So just add 1 onto both sides, and you then get that n plus 1 is greater than s. And n plus 1 is going to be a natural number as well. So now that contradicts s being an upper bound of the natural numbers. So total contradiction. So it can't exist. You can't have an upper bound to the natural numbers. A beautiful little proof that follows straight from the completeness axiom. So back to limits. So this is not a good definition. This is a bad definition because if we took this as our definition, then it would be true that the limit of this would be equal to 0, or 0 would be a limit of this, but we don't want 0 to be a limit of this. This sequence should have no limit. So what went wrong here? So at the moment, all this definition says is that the terms of the sequence need to get indefinitely close to the limit. The problem is the terms of this sequence do get indefinitely close to 0, but the problem is that at the same time, we're continuously flitting back to 20. So we've got these terms of the sequence that are getting indefinitely close to 0, but in between each one, we're flitting back to 20. That's the problem. That's what this isn't capturing. Really, for a sequence to truly have a limit, it needs to be the case that the terms of the sequence don't just get indefinitely close to the limit, but they also have to stay indefinitely close to the limit. That's what wasn't happening here. Whilst some of them, half of them were getting indefinitely close to the limit, we were also, the other half, were continuously flitting far, far away from it. So we weren't getting to and staying indefinitely close to the limit. We're just getting indefinitely close to the limit and not actually staying there. We were continuously flitting backwards and forwards, far, far away, very, very close, far, far away, very, very close. So we want to change this now so that it captures that the terms need to get indefinitely close and stay indefinitely close to the limit. So get to and stay indefinitely close to the limit. So here then is the final definition of how you define a limit formally, the epsilon definition. So however close you want, so for all epsilon greater than 0, there must exist a point in the sequence, which we call big N, such that at that point and for all terms after it, so for all little n is greater than or equal to big N, all of those terms of the sequence are going to be that close to the sequence. So an minus the limit is going to be less than epsilon. So a picture to motivate this then. And firstly, I'm just going to box that because that is the final definition. This is what it means for that sequence an to converge to the limit L. And green actually is a very nice bright colour. That shows up quite well. I might actually stick with the green pen for a bit. So, if we have our limit L here, and we have our sequence, A1, A2, and let's say it is converging on this picture to the limit L, so here's A4, and then I'm going to stop actually writing them down, but they're getting indefinitely close to that limit L. I'm also going to write down, whoops, don't know what went wrong there. Let me rub that out. And I'm going to go back to white. I got fed up with the green pen. It's a little slimy. So A1, A2, and we go on to the general term AN, and I'll leave some space there. So what this is saying is if it is true that the limit of the sequence is L, then this should be true indeed. There's a biconditional. This is the definition. If this is true, then you can write that. If you write that, it better be the case that this is true. And what this thing means is that however indefinitely close you want, so for all closenesses, so for all epsilons, that's what the epsilon is, it's closeness. So for all the closenesses, however close you want, so this is the epsilon interval around that limit, so the interval L minus epsilon to L plus epsilon, there should be, for each one of these, and it will depend on the epsilon, this big N, so if you give me a certain epsilon, let's say you set epsilon equal to 1/2, I will find you a big N. If you make epsilon much smaller, a million, 1 over a million, I mean, you'll have to find potentially a much, much bigger N. So this isn't a fixed N, but for every closeness, you should be able to find a big N, a point in the sequence. So there should exist a big N, which is a point in the sequence, so that's some term, a big N here, such that for that term and for all the terms after it, so for all the little n's greater than or equal to big N, so these are all of these terms after it, so this is n greater than or equal to big N, all of those terms should be within the epsilon interval, and that's what this is saying, that the distance between the term and the limit should be less than epsilon I, it should be within the epsilon interval. So all that is saying is that for however close you want, there should exist a point in the sequence where for that point and all the points afterwards, they are that close to the limit. And that now is capturing this concept of the terms of the sequence should get to and then stay. That's this bit. That's the correction that wasn't in here, that all the terms afterwards should also be that close. So it should get to and stay as close as you like, indefinitely close. For all closenesses, it should be true that there exists a point in the sequence where they're all forever after that close to it. So that is what this is saying. So we'll end the video by doing just a quick example, and we'll do the example that we've been using throughout the video, the harmonic progression. Now, I feel a little guilty because it is a very easy one to prove this for, but I feel justified because we've used it throughout the video. So we'll do this. So we have our sequence 1 over n, and we want to prove that its limit is at n approaches infinity of indeed 1 over n is equal to 0. We want to prove that it satisfies this new definition. So drawing a picture again, we have 0 here, we have our first term here, 1, we have our second term here, a half, third term here, a third. And we want to prove that the terms of this sequence get to and stay indefinitely close to that limit. So we will let epsilon be greater than 0, so we're assuming a general epsilon greater than 0, and we will show that you can find a big N such that this property holds true, and as we've taken a general epsilon greater than 0, it will then hold for all of them. So we want to find then, our job is find big N is an element of the natural numbers such that for all the little n that are greater than or equal to big N, the distance of an from the limit is less than this epsilon that we've started with. So let's consider what the distance of the term an from the limit is. Well, the limit is 0, so that makes things simpler. So actually, this distance is just mod of 1 over n, which is just equal to 1 over n. So we need to find some big N such that for that term and all the terms afterwards, 1 over n is therefore less than epsilon. Now, can we do that? Well, we can, again, just by the Archimedean property. So we can rearrange this inequality to see that this will hold true for all n that are greater than 1 over epsilon. And again, by the Archimedean property, the natural numbers are not bounded in the real numbers, so they're certainly not bounded by whatever 1 over epsilon is. Now, epsilon could be very small, so 1 over epsilon might be massive, but there will be a whole bunch of natural numbers after that. So on a picture, here's 0, here might be a tiny little epsilon value, and now the multiplicative inverse of epsilon might be something massive over here, but then after that, there are a whole bunch of natural numbers going on forevermore. And all of those natural numbers are going to now satisfy this property, and therefore they're going to satisfy this inequality as well. So for all of these natural numbers that are bigger than the multiplicative inverse of epsilon, if you were to take their multiplicative inverse, so let's say if I was to grab this one here, if I was to take its multiplicative inverse, it would now be even smaller than epsilon. That's the crucial thing here. So this thing, its multiplicative inverse would be less than epsilon, so it would satisfy this inequality here. So to find my big N, I just need to make it actually one of these natural numbers that is greater than 1 over epsilon. Now the most elegant thing to do would be to pick the first one that's just above 1 over epsilon, so this one that I've marked in red. However, I don't even need to do that. I could actually pick any of these, so I could pick this one, and then it will certainly be true, if I take, for instance, this as big N, that for all of these little n's that are greater than or equal to big N, and again, red is not showing up well. I'm going to rewrite that in white just in case it doesn't show up. So for all these little n's, all these other natural numbers that are greater than or equal to big N, it will then still be true that this inequality holds true, and therefore that this inequality holds true. So that's the proof that you can find big N. So for any epsilon, all I need to do is find its multiplicative inverse, choose some big N, which is a natural number that's bigger than that 1 over epsilon, which I can always do by the Archimedean property. And then because of the way it works here, it's then going to be true that all of those natural numbers that are bigger than it will satisfy that inequality, and therefore will satisfy this. So this whole thing will then be true. So quod erat demonstrandum, we did that for a general epsilon, and therefore it's true for all epsilon. So yes, it is true that the terms of this sequence get to and stay indefinitely close to the limit. And on this initial picture, actually, that's really quite intuitively obvious. You know, I can put whatever epsilon interval I like around here, so negative epsilon to positive epsilon, so however close I want to, and we can see that the terms of this sequence are monotonically decreasing. Every successive one is smaller than the previous one. So all I need to do is find one term that's inside here, which I can always do by the argument that I've got here, because there is always going to be a natural number that's bigger than the multiplicative inverse of epsilon, and therefore its multiplicative inverse will now be smaller than epsilon. So I just need to find one that's inside there, and then it will then follow that all of the ones after it are also inside there. So it is satisfying this property that they get to and stay indefinitely close to the limit. So we'll end there. Thank you for watching.